In general, a probability distribution starts from a set of objects or properties or events or whatever it is that we are working with and assigns percentages to them. For example, the probability distribution of a non-biased die assigns a sixth of probability to each one of the 6 possible outcomes. Or a probability distribution of ages for a certain population can assign the frequencies with which people are observed in each age range. Or a model that classifies images of patients trying to detect certain pathology can give us an estimation of the probability that a specific case has or doesn't have that pathology. By consistency, we usually express the probability with a number between 0 and 1, sometimes also between 0 and 100. And there are 2 properties that any probability distribution should always fulfill. This number must always be between 0 and 1, of course, and the sum of all probabilities assigned to all the objects that we are considering must add up to 1. And this sum will probably be an integral if we are talking about continuous probability distributions, as we will see later. But one very important thing to keep in mind is that not all probability distributions have the same meaning, and we have to know what we are representing with a probability distribution to be able to manipulate and handle it properly. For instance, a probability distribution can describe all the possible sums of 2 dice thrown at random. In this sense, there are 36 possible combinations, of which, for example, only one of them adds up to 12, only another one adds up to 2, there are 6 combinations that add up to 7. In general, for each possible value between 2 and 12, possible outcome, there is a probability that represents how many combinations can generate that number. So in some way, this probability distribution is describing a reality, some combinations of outcomes. We could also use a probability distribution to communicate the results of a population census, or perhaps a population survey. Note that in these cases, the distribution does not represent an ultimate reality, but an estimate of the reality, and depending on the procedure we have followed, this distribution will be more or less close to reality. Perhaps we can consider an estimate from a census a much closer thing to a reality because it is more exhaustive, and we might also take an opinion poll with more caution depending on how the survey was done, how the participating people was selected, and we can have more or less confidence in it depending on how it was generated. But what the probability distribution represents is the result of the process, whatever that process is. Or for example, we can also represent with a probability distribution the degree of knowledge of uncertainty that we have about something. And then we can update it as we learn new things, we gain knowledge. It can represent, for instance, my ignorance of whether it would rain or it would not rain, assigning a 0.5 to each case as meaning that I don't know anything. Or if I look out of the window and I see clouds, then maybe I change that assignment so that I update the probability distribution so that 0.7 is assigned to the case with rain. In this case, the probability distribution is representing something subjective. It's representing my knowledge of uncertainty of something. And this corresponds mostly to a Bayesian approximation, for which Bayesian statistics has its specific mechanics and procedures in order to be able to manage in a mathematically consistent way all these updates, these transformations of the probability distributions as we acquire new information. And for instance, what would represent the probability distribution that a predictive model assigns to the image of a patient, as we said before, about whether the patient has or doesn't have a pathology? It is actually an estimate, a calculation, that again can be more or less close to reality depending on many things. For instance, if the data with which the model was trained was not enough, or if the model is too complex, or is it too simple, or if the pathology maybe is intrinsically difficult to separate, or many other circumstances. In any case, the probabilities that a model assigns to a certain case represent a calculation, and we have to interpret it and handle it as such. There are many circumstances that we represent with probability distributions with many different meanings, and we have to be aware of them. In the case of machine learning, we would like to do several things with probability distributions. One of them is to properly deal with the uncertainty that surrounds any process dealing with data. Maybe that the data that we have has a natural randomness that we cannot get rid of, and we just have to learn how to handle it in a coherent manner. For example, because we have noisy sensors, or because the populations that we have is mixed, as we have the patients above. Maybe the pathologies that occur in different patients are not easy to separate, as we said before. And we would like to be able to manage this properly, in the sense that our models respond differently if the uncertainty surrounding the data is greater or smaller. But it could also be that the uncertainty is introduced not by the data, by the nature of the data, but by the model itself, due to the way in which the parameters of the model capture the relationships between the data. Perhaps the uncertainty is actually coming from the way in which parameters themselves are generating a certain prediction. Like complex models generate different distributions of predictions than simpler models. And all these uncertainties are actually what we want to be able to handle with probability distributions, and with specific mechanics on how to transform and handle those distributions. If you think of it, every time we have a number, a parameter, a weight, a measure, or something, we could have instead a probability distribution that represents our uncertainty about what that number is. Or even when considering the weight of a connection between two neurons in a network of artificial neurons, instead of handling it as a single number, we could think of it as a distribution of possible values for that connection, which of course it is something much more complex, much more rich. And what is the challenge that we are addressing in this course upon these kinds of situations? The main point is that a probability distribution is something much more complex than a single number. A number is a scalar, a quantity, but a probability distribution is, as we said at the beginning of the video, an assignment of probability percentages to a population of objects described with numbers. What we have to understand is that when we deal with probability distributions, what we are actually dealing with are populations of things, and transformations of these populations based on the processes that we do. And these populations will be representing different things. Our certainty of something, the possible values of weights that we are considering for a certain connection in a neural network, the mixture itself of the data, the random noise of the instruments of measurements of the data, and so on. Therefore, we are going to have to generate all the necessary machinery to manipulate, process, transform, combine different probability distributions. Simply to get a little bit of an idea of the complexity that we are facing, imagine that we have a neural network in which each weight is a probability distribution instead of a number. In this case, how should we generate a prediction? And what is actually a prediction? How is each output neuron going to generate a probability distribution? What would it represent? How would you train finally the network knowing that its connections are represented by probability distributions and not by number? How do you apply gradients and so on?